I started my career at Silicon Graphics in 1999, and around 8 years, I took over the vertical role of focusing on computer-aided engineering. And then a couple of years ago, HPE bought Silicon Graphics, and I was really excited that I think it was about 18 months ago, 2 years ago, HPE also bought Cray. So you could see sprinkled through these different slides that Wim provided that HPE, SGI, Cray has really been working with Ansys for, I think, over 20 years, if you really look at it, and I've been doing it for 8 years. And I'm also excited to be working with AMD. I'm old enough to see when Opteron came onto the scene, how it took the CAE world by storm. And then the EPIC architecture, especially the second generation and now the third generation for CAE workloads, I was really excited to see how we were going to pump up the performance and really help with that. So I'm here with Kevin Mayo. I'm going to share a couple slides on how we partnered together to enable Ansys applications. So Wim talked about the different physics that are being deployed to do virtual prototyping. And so those boxes that have computational structural mechanics, there's two types. There's the implicit and the explicit. The implicit is using a software, Ansys Mechanical, and the explicit software is LS-DYNA, also recently purchased by Ansys. It's one of 3 crash simulation codes that are out there in the marketplace. We also heard from Michael and from Wim about computational fluid dynamics, CFD. They're highly scalable code. Ansys Fluent is shown to run on to 200,000 cores. The KAUST supercomputer in Saudi Arabia is a Cray system, now an HPE system. And SGI and Cray traded world records over the past 6 or 7 years, trying to work with Ansys to expand Fluent. And we also worked with Ansys to really look at the large size of the models, degrees of freedom, and cell models. And we've been able to run, 1.5 billion cell up to 2 billion cell models on high performance computers running Fluent. CFX is another one of their solvers that Wim talked about. In the computational electromagnetics, or CEM, Ansys has a high frequency software called HFSS, and then their low frequency electromagnetic code called Maxwell. At SGI, we worked with Ansys to really make HFSS NUMA aware, so that's where they can see multiple nodes, more than 2 nodes in a socket. You can have 4 nodes or 8 nodes or more to really take advantage of large memory. HFSS is a memory maven. It really takes a lot of memory, and so we did that in 2016-17 timeframe, and I think as of Ansys R18, the NUMA aware in the Linux version of HFSS has been made available. And then with Ansys Maxwell, several years ago, Maxwell didn't scale. It was really run on maybe 8 or 16 cores, and they came up with what they call the time decomposition method. And SGI at the time worked with them to run large-scale benchmarks to really show the value of time decomposition method. Ansys Workbench is a workflow, and Ansys Minerva is simulation data management. So we support both of those protocols and software. And so that's really the heart of the solution, is really to make sure that the Ansys software and infrastructure runs as effectively and efficiently as possible. And to do that, we build a stack, starting at the bottom, our compute and storage solutions, and a parallel file system, a 64-bit OS, could be Slurm, or I'm sorry, could be SLES or RHEL. And then we have a whole series of our own high-performance computing software stack that then supports a workload scheduling tool. So for those panoramic studies that Wim talked about, being able to send multiple simulations to a large cluster at the same time is through that workload scheduling tool. And then on the top is high performance remote visualization. So you're going to do some pre-processing of those simulations, and then once the simulations have run, you want to do your post-processing. Your engineers are going to want to really dig into and look at the visualization of this final run to make their decision on the design. And if they need to run it again, then they take it through the whole system. And then on the right, we have a technical group, our partners, and our Point Next can bring all of this together for our customers. So to really take advantage of simulation software from Ansys, really the solution has to hit these different marks. It has to be a scalable cluster, so it's beyond the workstation, so it could go to one node to thousands of nodes and anywhere in between. I think Wim talked about and Michael talked about the need for high frequency CPUs, more large core counts, and large memory capacity. The bandwidth, memory bandwidth is key, as it's been mentioned already, and the I/O, and the low network latency. So we support InfiniBand. We also have, through our Cray acquisition, the Slingshot interconnect. And really what you want to do is make sure that your system is up 24 hours a day, 7 days a week. So better RAS is very important. So that all feeds into what I'm showing on the right, which is just a more abstract of what the slide I showed previous. Deployment model. So what I like about HPE, we're a very big company. So we actually have our own financing arm. So a customer could say, look, you know what, I'm going to buy a cluster, I'm going to manage it myself, I'm going to just pay for it as a capital investment, and that's great. They may say, you know what, I want to lease the equipment, and after 3 years, I'm going to have you take it away, and I want to bring in the next best technology that's along the way. So we have leasing options. We also have what we call flexible capacity. So our GreenLake group could say, you know what, we'll put in 2,000 cores, but we're going to add another 500 cores. That's just there. So if you need a bursting capacity and you don't want to go to the cloud, you want everything to be the same, but you're only going to pay for what you use over that 2,000 cores, we have that capability as well. And then we also have this slide where it's a fully managed, pre-bundled HPC private cloud service. And so there we have small, medium, large standardized HPC clusters that are tuned for CAE applications from Ansys. You can order it and it quickly arrives. We then deploy that and basically we manage it for you, and you have a point and click experience, and you can grow that solution over time. So that really is a full spectrum. We also allow, if you want to burst to the public cloud, that's no problem as well. So we can then provide that bursting capability into the public cloud. So I'm now going to turn it over to Kevin just to kind of reiterate the performance value of the AMD EPYC. This is the second generation codename Rome, or the Zen 2 cores. Kevin?
Hi there. Thank you, Tony. Give a second to confirm if you can hear me okay.
I can hear you.
Okay, perfect. Okay, thank you, Kevin Mayo with AMD, and I'm responsible for our HPC solutions engineering team, working with folks like Tony and Wim. And wanted to just start off by saying what great partnerships we have with both of them. Outstanding companies to work for, very focused on the end customer, and that aligns well with where AMD sees itself, and so fantastic partnerships. So from a performance standpoint, actually, I might take a step back for a second, and realizing that this is not a typical HPC audience, maybe where people may be less familiar with the workloads, and as I was listening Michael and everyone else talk, I think some of the one example I like to bring up is not only are you looking at things like crash simulation that are life critical workloads and structural analysis for bridges and things like that, and Formula One, computational fluid dynamics to make the Formula One car more efficient and competitive. So all very kind of somewhat exciting use cases. It much broader than that. So if you think of even a consumer packaged goods, I think Mike used that as an example. Think about a shampoo bottle, using fluid dynamics to make sure you efficiently fill the shampoo bottle with shampoo to make sure that you get the right amount and it's your manufacturing line can go fast. Not only that, but pouring in the plastic to make the bottle in the first place, making sure that goes efficiently to make the bottle. So those would be examples of CFD, fluid dynamics kind of applications. And then you might use FEA implicit from a structural standpoint to make sure that when you stack those bottles up and put them on a pallet and rack several layers of bottles, that those bottles have the structural integrity as a unit to not collapse. So things like that, where you're dealing with just the kind of static structures of the product. And then stand in the shower and drop the shampoo bottle and make sure it doesn't break. And so that would be a use of FEA explicit, like the car crash simulation. So these workloads that have these very kind of exciting use cases also have what you might consider a dull use case, but to those companies just as critical. Focus on the bottom line, focus on the ecological things such as using less plastic in their bottles. Minimize the amount of plastic you need to put into the bottle to make it have the right structural integrity and to make it have the right impact resistance. So just to share a few use cases there that don't necessarily always stand out, and I'm amazed every day, even working in the market here, amazed every day at different workloads that I didn't realize they put so much computation behind.
So Kevin, the classic that I was working with at Silicon Graphics was Pringles, and so everybody kind of looks at, well, how did those chips get into those tubes? Well, the whole saddle shape of the chips were designed, through simulation, and getting those chips into those tubes was definitely a computational fluid dynamics problem. So yeah, it's definitely,
they're kind of blown, aren't they blown in?
Yeah, they're blown in. Yes.
Yeah. I didn't realize the chips were designed with that curve in order to make that happen. So that's I like that. Okay, so jumping to performance, this first slide is actually looking at our second generation of EPYC. So you kind of recognize those with all the model numbers ending with the number 2. So second generation. So in this case the 75F2, which is our performance optimized part with the F in the model name, and the 5 in this generation indicates it was our 32 core. I'm sorry, the 5 in this case is our 24 core part. So a 24 core part versus the Xeon 6246R. So several workloads we've talked about, Fluent being the kind of standard CFD, CFX being the turbo machinery focused CFD application, and then LS-DYNA being the kind of dynamic or car crash simulation and that kind of thing, kind of dynamic structural situations. Very, very good performance, 24% on Ansys, largely attributable to the, as Wim mentioned, the memory channels and the high cache. CFX is similar, but you can see it really stands out performance-wise, and that is very directly related to the cache size. It has a very bandwidth and cache, so the memory channels have a big impact, but it really does like the cache size and stands out very high from a performance standpoint. LS-DYNA as well, very, very good performance in that Rome generation versus the same generation of our competition. So kind of across the board, really solid performance. So next slide. And I believe Michael talked about this, but just to hit a few highlights of kind of coming from second generation back into the third generation. The biggest change, of course, is our Zen 3 core. So generationally, that core design had some major revisions, and I believe somewhere in the 19% IPC instructions per clock, kind of measure of efficiency and compute power, generational jump, and that's across a 28 or so workloads that we averaged, just to get a ballpark good average of IPC uplift. The memory performance, not only we still have 8 channels of memory, we still support DDR4 3200 DIMMs, but we've sped up with this generation. We're able to push the frequency of our IO die in order to get the fabric clock, the fabric that moves the data around from core to core and cache to cache, to get that clock up to match the DDR frequency. And so where we were slightly below, now those match, and you get very efficient data movement from memory into the core. You don't have to trade off between bandwidth and latency when you're looking at fine tuning performance, and so that's very good. And then the cache itself, we did the total cache size stays the same at 256 on our largest processors, but instead of that being split into 16 megs per 4 cores, it's now we've merged those two, so we have 32 megs per 8 cores. So changing the kind of radius of that cache sharing has had a big improvement. Quick note on security features: HPC is not necessarily always known for worrying about security. Typically have clusters set off to the side and not exposed to the outside world, so they don't have to apply the latest security patches and that kind of thing. However, moving into the cloud is one good example, and then also a few areas where, like financial services, where you might be actually more worried about your code than the data itself. You're more worried about the proprietary algorithm that you have, and so moving into the cloud or on-prem. We have some unique security features that can isolate your VM from everyone else, even the cloud provider. So several different cloud providers have started offering that feature. So that's an interesting one to look at if you have a security sensitive application or data set. And then we're backward compatible, so platforms designed for our second generation. Also, we can drop in the third generation, and you do need a BIOS update. The provider, like HPE, provides a BIOS update that then will work with the third generation processor. So it's a very good compatibility. Makes it cheaper for customers, makes it cheaper for OEMs and everyone to be able to leverage that same infrastructure and still get great improvements in performance generation to generation. So we try to do that when we can. Can't always do that because technology changes, but when we can, we try to do that. So jumping into this is our third generation. So this is our latest and greatest. Here we have our 75F3, which is our 32 core processor. And this is against the second generation Intel Xeon. So they just came out with their codename Ice Lake, kind of third generation, but we haven't started shipping those yet. So we don't have any of those in house to test with. So the latest that we have is their second generation. So we've got the 28 core, which is our highest core count, and the highest frequency at that core count. And so that's what we've compared with here. So our third generation versus that baseline, 43% in Fluent, so a step up from what we saw before. And this is actually even against a faster higher core count part than on the previous slide. CFX jumps up to 85% faster. That really, some of the individual workloads go up to 100% faster. So very, very good. You can't ask for much more performance uplift than that. There's extremely good performance there. And then 68% on LS Dyna. So don't know what else to say except just to put those numbers on the screen and point to them and say just outstanding performance. Just head to head kind of fastest part, and we're anxious to test Ice Lake performance and see where that lands, but feel very, very good about where we are from our performance standpoint.
Yeah. So I'm sorry, go on, Kevin. I was just going to comment something, but go on.
Oh no, go ahead.
No, I was going to say, what you're really delivering is, if I had an Ansys a license, 3 years ago, that same license is delivering 85% more simulations. I mean, that's the thing that gets me excited for our customers, our joint customers. They're really going to be able to take advantage of the software investment that they have based on the performance uplifts that we're seeing with this third generation processor. So.
Yep, that's a very good point, right? Ansys is on the leading edge of innovation and driving fantastic performance, and that comes with a license cost, right? And so if you have that and you've got a workload, you've got to get through either a certain amount of kind of time to solution. You want to squeeze your start to finish time, or as Wim stated, kind of get more granular and run finer grained models, being able to
Yes.
optimize on either of those and more efficiently use your licenses. You can take those licenses and run more throughput or finer grained models, either or, and do fantastic performance.
Yes. Yeah, choice. It really gives you the choice.
Yep, absolutely. And so I think that maybe the last slide I have, just want to give you a little. I think Wim had some good detailed slides on performance, but I'll turn it back to you, Tony, to wrap up, or we can go back to run.
Yeah, I just had to show these end notes. That's what you guys need to do.